Good morning, everyone. My name is Satisha, daughter of Chandrasekharan, and my metric number is 06DKA21F2019, and I am from DKA 3A. So, today we are here to present about Chapter 3, which is Flow Visualization, and in this presentation, we are going to state the Reynolds numbers formula, limiting value of Reynolds number, calculate the Reynolds number, and finally explain laminar flow, turbulent flow, and transition flow. So let me present about the introduction and overview of the topic. The bulk dynamic of the ultra relativistic heavy ion collisions have been successfully described about the hydrodynamics. We give the fundamentals to the theory of viscous hydrodynamics in this sufficient study. Hydrodynamic, the numerical application of relativistic hydrodynamics and the derivation of the second order viscous hydrodynamics from the linear response theory and kinetic theory among them subject discussed.
Good day, I'm Vishwadan here to present about the question given to me, which is flow visualization, and I'll be going through the respective topic by explaining it in three aspects. The first one is what is flow visualization or the introduction towards it. Secondly is the common experimental method of flow visualization, and finally is the importance of it. But before that, I think it's important for us to know and understand what is flow. So basically, flow means the displacement of certain molecules, because displacement of molecules from a point to another point is what forms the flow. And this happens only when an external force is acting upon it, because otherwise if all forces were at equilibrium, then there will be no flow, isn't it? So in other words, we could also say that flow is the motion of atoms due to the presence of shear stress. So now that I've made it clear about what is flow, we shall get into the respective topic of flow visualization. Flow visualization means the art of making flow patterns visible, because not all fluids can be visible to our naked eyes, isn't it? The concept of this study can be explained with an example. So if you were to witness a fish moving its fin in an aquarium, right? Can you tell about the flow patterns around the fish? Obviously not, right? But let's say if you were to drop a small twig or a leaf close to a fish, you could have a basic understanding about the flow patterns around the fish, isn't it? Based on the movement of the twig or the leaf, right? So the concept of flow visualization is something very similar to that. It provides us with qualitative or quantitative information of flow patterns. Broadly speaking, visualization technique can be classified as experimental and computational. Computational methods is by conducting an experiment by a computational simulation, while experimental methods are by manually doing it. So for example, the example that I gave you earlier about the fish in the aquarium can be said as an experimental method, because that is something that we do manually, right? However, there are many types of experimental methods, but they may be time-consuming, less accurate, and cost a lot of money. But anyhow, with that being said, I'll just move on to the second aspect of the presentation and talk about the experimental methods. So for that, I've got this picture with me of an aeroplane which is flying with two different kind of flow visualization techniques. First of all, if you can see, there's this smoke from the head of the plane moving towards the bottom, and that's an example of straight line. So straight line is something which connects all the particles which flow through the same point area. So all the particles from this edge flowed all the way down, picking up some smoke. By the way, the smoke is something which is deliberately made so that the flow is visible, and that is a straight line method. So for the next method, right, as you can see, there's all these little strings glued all over the aircraft, which gives the velocity of the surface of the aircraft. It helps to point out the direction of velocity vector actually. If in case you're wondering how, right, then if I were to simply draw a line connecting all those strings, tangent to all those strings, as you can see, I'm able to map out the direction of wind flow. And that's a technique called streamline. So now we have seen two different kind of technique, which is streamline and straight line. There are many more techniques actually, but then I wouldn't want to feed more. With that, I'll just move on to the final aspect of the presentation, which is the importance of flow visualization. And in pursuit of that, I would like to share a video. And so what you're looking at right now is the same aircraft, and if you can watch closely, you may see the vertical tail wing is vibrating, and this is because of the tension caused by the airflow. As you can see, the air at the straight line, right, is causing it to move back and forth, which is problematic as it may lead to fatigue in the vertical tail wing. So back then in the 1980s, right, engineers were figuring out an appropriate modification that could eliminate the vibration. So with that being said, I think it's already self-evident of how important flow visualization methods are to come up with decent models or to identify problems and to solve them. However, the methods of flow visualization are also being used in various fields of studies. For instance, even in the medical field, right, visualization methods are used to track blood flow and to cure complications. So I hope that you have a basic understanding now of what flow visualization is. So that's all from me.
Hello everyone, my name is Avinash Jendran. My meeting number is 060K21 F2030. So here I'm going to present about section B, which is Reynolds number. So what is Reynolds number? Reynolds number is important in analyzing any type of flow. So the function of Reynolds number is to get some sense of the relationship in fluid flow between initial forces, that is those that keep going by Newton's first law, and object in motion remains in motion, and viscous forces, that is those that cause the fluid come to a stop because of the viscosity of fluid. So first of all, we like to see the limitation of Reynolds number. Okay, before that we should know the three types of flow, that is laminar flow, translational flow and turbulent flow. Laminar flow is below than 2300. Next is translational flow. Translational flow is between 2300 to 4000, and the thirdly is turbulent flow is above 4000. Secondly, we like to know the formula of Reynolds number. Okay, Re equal to Vd over V. Re is Reynolds number. So what is the Vd over V? Vd is velocity of fluid times by diameter of pipe divided by kinematic viscosity. This is the formula to find Reynolds number. Okay, next we just see an example question of Reynolds number. Okay, I read the question first. A liquid is flowing through a pipeline of 4 cm diameter. The dynamic viscosity of liquid 8620 times by 10 negative 4 ns per meter square, and the specific gravity of the liquid is 1.25 with the velocity 32 cm per second. So calculate the Reynolds number and types of flow. So we would know the points first. Okay, points that given, velocity of fluid that they given is 32 centimeter. Make sure we would convert centimeter to meter. Okay, so 32 centimeter is convert to meter is 0.32 centimeter, and specific gravity is 1.25. To find kinematic viscosity, dynamic viscosity divided by density, so we can get kinematic viscosity. So specific gravity can change to density, so times by 1000 we can get 1250 kg per meter cube. Okay, so the diameter of the fluid is 4 centimeter. To change to meter is 0.04 meter. Okay, to find the kinematic viscosity is dynamic viscosity divided by density. So dynamic viscosity, it's already given 8620 times by 10 negative 4, and divided by density is 1250. We can get easily kinematic viscosity. So after we find the kinematic viscosity, we just apply Reynolds number formula, which is velocity of fluid times by pipe of diameter divided by kinematic viscosity, which is 0.32 times by 0.04 divided by 6.9 times by 10 negative 4. So the answer will be 18.55. So the 18.55 is a type of laminar flow because it is below than 2300. Okay, lastly I would like to explain the three types of flow. Okay, first one is laminar flow. Laminar flow that type of flow in which the fluid particles move along well-defined path or streamlined, L the line or straight and parallel. Okay. Second is turbulent flow. Turbulent flow is the type of the fluid particles move is a zigzag way. The fluid particles crosses the paths of each other. Okay. Third one is transition force. Mixture of laminar and turbulent flow with turbulence in the center of the pipe and laminar flow near the edges. Okay, each of these flow behave in different manner in terms of their frictional energy loss while flowing and have different equation that predict their behavior. So this is the difference and explanation for three types of flow.
So next about the conclusion. As a conclusion, by determining the kind of flow using the Reynolds number formula, we have used hydrodynamic to track the energy held in the medium. This helps to guarantee that the work has not failed as a result of incorrect prediction.